Welcome everyone to this explainer. Today, we're going to do something a little different. We're going to completely slow down time to investigate the hidden microscale drama happening right inside your everyday electronics. We interact with switches and buttons countless times a day without even a second thought. But beneath that totally simple physical action lies a genuinely fascinating world of physics, electrical engineering, and rapid-fire logic. So, let's uncover the secret life of a switch. Okay, let's dive right into this mystery. You push a button, and boom. It seems instantaneous, right? The light just turns on. But what's actually happening in those microscopic milliseconds before the light comes on? To figure this out, we're going to look really closely at a basic Arduino circuit and trace the exact chronological timeline of one single button press. We're going to stretch out mere fractions of a second to witness this hidden war between hardware chaos and software order. All right, phase 1, boot up or setting the stage. Right when you first plug in or reset the Arduino. Right out of the gate, there's this incredible tug-of-war happening before you even touch a thing. On one side, you have the hardware state. The command pin mode input pull-up activates an internal resistor that essentially pulls pin 2 up to a high state of 5 volts. On the exact opposite side, we've got the code state. The variable LED state initializes as low, and digital write runs just once during setup to enforce that. The result of this little standoff, the physical LED remains completely off. Now, while that light is off, you'd totally be forgiven for assuming the system is just taking a nap. But consider this number: thousands. The system is actively waiting and scanning pin 2 thousands of times every single second, just hunting for any tiny change in that 5-volt baseline. It is highly alert, checking over and over and over again, ready to spring into action the absolute microsecond you decide to push that button. Which brings us to phase 2, the first button press and the actual process of turning the light on. When you finally push and hold down the button, you physically bridge a gap. Completing that circuit to ground forces a massive, instantaneous drop in voltage. Pin 2 plummets from a high 5 volts all the way down to absolute 0, a low state. The trap has been sprung, and the Arduino registers the drop. But here's the catch: the physical world, it's incredibly messy and chaotic. When you press a physical button, those tiny metallic contacts inside don't just gracefully connect once. They actually smash together and violently vibrate or bounce on a microscopic level. If the code didn't account for this, your single press would look like you furiously mashed the button dozens of times in a millisecond. To solve this, the code has to act as a debounce filter, cleverly ignoring the mechanical noise of those bouncing metallic contacts. So the real hero here is this specific line of code: if reading does not equal last button state. This little snippet acts like a detective. It detects the instability of that bouncing metal. Every single time the voltage bounces up and down during that chaotic impact, the code catches the discrepancy and stubbornly resets its internal stopwatch. It's basically saying, nope, still bouncing, restart the timer, continuously resetting it using the millis function until the violent bouncing finally actually stops. And what exactly is it waiting for? 50. The code sets a strict debounce delay window of exactly 50 milliseconds. It's programmed to simply wait out the mechanical noise. The system demands a solid, uninterrupted 50 milliseconds of pure silence, a stable 0 volts, before it will actually believe that you intended to press the button. Tracking this in a slow-motion timeline, the whole sequence is wild. First, the signal violently plummets to 0 volts as you make contact. Second, the chaotic metal vibrations totally confuse the electrical signal. Third, that agonizing 50 millisecond wait happens as the debounce filter does its job. And finally, we get the lock-in. The code confirms a truly stable low state. Only then does it decide to turn the LED on. And this brilliantly illustrates the absolute magic spell of the code. Once those 50 milliseconds pass, and the system is completely sure of the button press, it triggers this beautiful line: lead state equals not lead state. This is the toggle. Since the state was previously sitting there at low, this command instantly flips the memory state to high. Finally, the physical output catches up to the software logic. The digital write command executes for high, and the LED bursts into light. And here's a really fascinating extra detail. Even when you release your finger and the physical metal separates, causing the signal to shoot back up to 5 volts, the code is smart enough to completely ignore it. It doesn't turn the light off, because it's strictly programmed to only care about that specific, stable transition down to low. Now, let's look at the second strike in phase 3, the second button press, and the process of turning the system back off. Turning it off is basically déjà vu. It perfectly mirrors our first sequence because the system identically repeats that whole debounce filtering process. You press the button, pin 2 drops to 0 volts, the code plays detective again, waiting out the chaotic 50-millisecond mechanical noise window. It sees a stable low, but this time, because the memory state of the LED was currently high, that toggle command, lead state equals not lead state, forces it to flip back to low. The logic has completely reversed. Which triggers our final command, digital write low. The LED is instantly plunged back into darkness. This final execution is absolutely the ultimate victory of software, bringing perfect, predictable order to the messy, vibrating chaos of physical hardware. As we wrap up this explainer, take a second to just look down at your keyboard or your mouse or your game controller. I want you to ponder the literally millions of hidden battles happening right at your fingertips. Every single keystroke, every single click triggers this incredible, invisible 50-millisecond dance between vibrating metal and lightning-fast code. It's just a remarkable testament to how intricate our everyday technology really is. So, how many times has that invisible dance happened for you today? Thanks for joining me to explore the secret life of a switch.